All right, welcome back to probability modeling. Today we're gonna continue with our discovery of Poisson processes. I think we should have around 2 lectures left, and then we'll be done. After that, I'll see what we do. Probably, revision and maybe going through old exams. But for now, for today, let's go back to the Poisson process. So first, as a reminder of what we did last week, we gave the important definition of what the Poisson process is, and I'll recall this now. So you're counting events which happen more or less randomly, and the way you count these events is with variables nuv, where nuv is the number of events which happen between u and v being times. And we say that it follows the Poisson process if we have two conditions, A and B. Condition A is that the number of events between u and v is a Poisson variable with distribution lambda times the length of the interval you're considering, so lambda times v minus u. And if we consider disjoint time intervals, then the events which happen in each of those are mutually independent. And these two things, if you have both A and B, this characterizes your Poisson process. And so we like representing them with this kind of figure. So whenever there's an event, the function, this is n of 0t, it jumps by 1. And as we've said, the lengths of time where it's constant, so between the jumps, they are called the inter-arrival times. So this is the first inter-arrival time, this is the second, this is the third. Rather, you should project them on this axis. All right, and they're called T1, T2, T3, and so on. So one thing we said last time is that you can't have two occurrences at exactly the same time. So meaning that these inter-arrival times, they're not equal to 0. If you have an event, you always have to wait a certain amount of positive time until the next event. And the first thing we're interested in today is this theorem. So that's very strong. It says that the inter-occurrence, same thing, inter-occurrence times, they're independent and all have the same distribution, which is the exponential with parameter lambda. So, let us actually get to proving this. Get the pen. So this is theorem 19. Is this? Yeah, we'll manage. The inter-arrival times, or inter-occurrence times, they're independent and have exponential distribution with parameter lambda. Proof. Well, we won't do the whole proof. We'll do, let's say, we call it a sketch. To do a complete proof, we need a little bit more theoretical machinery, which we don't quite have. But we'll get most of the meaning of the proof, so it's fine. Okay, let's start with T1. We're going to show that T1 has distribution exponential with parameter lambda. And to do that, how about we compute for a real number t, t positive, what's the probability that T1 is smaller than t? So what is the distribution function of T1? Well, for T1, I said bigger, but I wrote smaller. Let's go with smaller. Well, if t1 is smaller than t, it means that your first occurrence happened before time t, right? So it means that there is at least one event before t. So this is actually equal to the probability that n0t is bigger than 1. And since n0t is an integer, it's 1 minus the probability that n0t is equal to 0. And that we know what this is because this is a Poisson variable with parameter lambda t. So we get 1 minus exponential of minus lambda t. And here, this should ring a bell. We recognize that this is indeed the exponential distributions. We recognize the distribution function of an exponential variable with parameter lambda. That's exactly what we want. So this, we've already dealt with T1. T1 has the distribution we want. Of course, we want Tn for all n, and we want the independence. So how are we going to do this? For Tn, was this on the camera? Yeah, fine. For Tn, we will condition on the past. So we condition on the values of the previous ones, t1 dot 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 tn minus 1. And apart from that, we actually do the same thing. So what's the probability that Tn is smaller than a certain number t, conditionally on T1 equals a little t1, T2 equals a little t2, and so on, all the way until Tn minus 1 equal little Tn minus 1. So what I'm saying is I'm conditioning on the values of all these guys. I say, well, T1 is little t1, and so on. And of course, I should have said this is for all positive t, t1, t2, tn minus 1. But so, at this point, it's basically the same thing. So we know where the n minus 1th arrival is, and if we want the nth arrival to be before t, it's like saying probability that n, that we want that there's at least an arrival between the time t1 plus t2 plus t3 plus tn minus 1 and the time all of this plus t. So it's going to be a bit messy in the indices, but n t1 plus t2 plus dot 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 plus tn minus 1 comma t1 plus t2 plus dot 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 plus tn minus 1 plus t bigger than 1. And okay, so there's a lot of things in the indices, but remember the distribution of this variable is Poisson with parameter lambda times this minus that. So it's actually the same thing. because we have an interval with length t. It's the same thing as what we did before. Equals 1 minus e to the minus lambda t. Same as before. So, and notice that, okay, we get 1 minus e to the minus lambda t, so we get our exponential. Also, the values of t1, t2, tn minus 1 don't actually appear in this formula at all. So this gives us also the independence we want. So tn is exponential with parameter lambda and is independent of the previous guys, t1 dot 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 tn minus 1. And this ends our proof. So I did cheat at some point. I cheated exactly here. Remember I told you that we actually need a bit of theoretical machinery. This is because here I'm kind of conditioning on an event which has probability 0. Since these guys, these t1, t2, tn minus 1, we know they're exponential. No, we're basically doing an induction. I didn't write it, but we're doing an induction. So since these guys are exponential, the probability of this event happening is 0. So conditioning doesn't quite make sense in the way we're used to think. But okay, there's some theory hiding behind this, and it actually works fine. So we don't need to worry about that. Okay, that's our proof, or partial proof of this theorem. So now, yeah, we really have a convenient and quite powerful description of your Poisson process. We just say your Poisson process describes people arriving in a queue. Then what we're saying is that you wait an exponential with lambda amount of time, then one person joins the queue, then you wait another exponential with parameter lambda amount of time, then someone else joins, wait another amount of time with the same distribution, someone joins, and so on. So that's a really quite useful and powerful theorem, and you can use this to build your Poisson process, because we've said this is a definition of the Poisson process. We didn't actually prove that it exists, but using this we can now build it, which we don't really need to do here, but that's a good thing to think about. Okay, so this ends this section. Now we're gonna jump ahead and actually generalize a Poisson process with notion of a variable rate. So we can basically make this Poisson process more flexible and give it more, let's say, modeling power by allowing the rate to vary. So before we had lambda. Lambda was the mean amount of occurrences happening per unit of time. And now we're going to change it to lambda of t. So what's the point? The point is, for example, saying that, well, traffic is heavier at rush hours. So your bus, if the arrival of buses is modeled by a Poisson process, there's going to be more buses at times where we need them, so which are typically rush hour. So the parameter would be bigger at these times. Or if you're looking at radioactivity, which is also a thing you can use Poisson processes with, then of course, the more your isotope declines, the more particles you emit, the fewer you have to emit, so the rate will also become lower and lower. So, how do I define this? Well, it's not too complicated, we got to replace assumption A by a more general version. So remember, A was that the amount of occurrences happening in time interval are Poisson, and the parameter is lambda times the length of the interval. Now we're going to say that it's still Poisson, but instead of having lambda times the length of the interval, we're going to integrate lambda over this interval. So integral from u to v of lambda of t dt. Of course, remember that if lambda is constant, so if we had just lambda instead of lambda of t, we would integrate the constant over the interval, which means we multiply by the length, so we get what we had before. Also, this is still a good way of saying a rate, because if you look at a very small interval, then you lambda, assuming lambda is differentiable, then you would get, well, it's continuous, that's enough. If the interval is small, you basically get lambda times v minus u again. So it's, again, this notion of rate, average number of events over the unit of time. Okay, so B is the same, but A is replace v minus u times lambda by this integral of lambda. So this is a simulation of a Poisson process with variable rate. So what do we see here? We see that at the beginning, it increases quite fast, and then it starts slowing down. So the inter-arrival times, the beginning, are all quite short, and then they become longer and longer. And you can kind of see there's a curve, right? This kind of follows a curve. And if I'm not wrong, I need to check my sources. I think here lambda of t is probably 1 over t. I may be wrong, but the point is, you can see that lambda of t is decreasing. And that's all we need to know. So events are more spaced out at the end than at the beginning. At the beginning, they happen really fast. Okay, so as I said, we don't change assumption B. So we keep the independence assumption. And what is nice is that the additivity property of the Poisson variables still fits with all of this. So if I look at the number of events between u and w, and then split them if they happen before or after v, with v being between u and w, then the total parameter of the Poisson variable, well, the parameter of the total Poisson variable of all these events is the integral over the largest interval, and this has to be the sum of the integrals over the two smaller intervals. And you know, of course, that the ways integrals work is that indeed these two things are equal. I forgot what the name of that rule is, but you know what I'm talking about, so that's fine. All right, let's give a fairly arbitrary example. So I'm gonna use an example about email arrivals. Example 34, email arrivals. Suppose, so you have your email inbox. Emails arrive as a Poisson process. I'm going to write PP for Poisson process. This is a reasonably common thing to do. With rate function lambda of t is t times 24 minus t. And you're guessing, of course, that t has to be between 0 and 24. Okay, so of course, this means we're counting time as units of hours. So the basic time unit is the hour. And so what is this function? So t times 24 minus t, it's a quadratic and it hits its maximum at 12. I guess if you wanted lambda of t, it's something like that, and we have 12 here. So we're saying that emails are more likely you're more likely to receive emails around noon, and you'll probably receive almost no emails around midnight. So this would reflect human activity during the day. Obviously it's a made-up example, but something makes sense in here. And here's a question. So question, let's say A. What's the distribution of the number of emails you get before up to t hours, and B, what is the probability of having no emails between midnight and 2 a.m. Well, it's not too hard if we know our definitions. So as we said, replace lambda times u minus v by the integral of lambda. So for A, we get Poisson with parameter integral from 0 to t of t times 24 minus t dt. And we have too many t's. I'm going to say s, 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 ds. And so integrate that, we get, I think what I've been given, oh, fair, that's my bad. Let's divide all of this by 12. Let's divide all of this by 12. Now things will be nicer. So we have 2s. The integral of 2s between 0 and t is exactly t squared. And then we have minus s squared over 12. So when you integrate that between 0 and t, you get minus t cubed over 36. And so for B, so we're looking between 0 and 2 a.m. So probability that there are no such things. So we put t equals 2, so we get 4 minus 836. And we get the, okay, so it's the we get, so number of emails between 0 and 2 has, can you see what I'm writing? Yes. Poisson of 4 minus 8 over 36 is, believe me, it's Poisson of 34/9 distribution. And so the answer is exponential of minus that. E to the minus 34/9. And if you care, it's about 0.0229 dot dot dot. But the value doesn't matter. You can't read this. 0.0229 dot dot dot. But what matters is the exponential of minus 34/9. Okay. So that's just a arbitrary example of a Poisson process with a variable rate. Okay, let's go back to our slides. So we define the variable rate Poisson process. Now let's look at other things we can do with those. And so we have, as you can see, a section with 3 things: superposition, marking, and thinning. Let's start with probably the easiest, superposition. So sometimes there's going to be more than one Poisson process running. I don't know, you're at a bank and there's 2 queues, and we may be interested in them separately or together. And so the theorem is that if you have 2 independent Poisson processes, so N and M are independent, that's very important, Poisson processes, and they have their rates. The rates can be constant or variable, it all works. So since constant is a specific case of variable, let's just have a lambda of t for n and a mu of t for m. Then the sum is also a Poisson process, and the rate of that is the sum of the rates. So that's an easy theorem, and let's go through the proof because it's a good exercise, but there's nothing too crazy about this. So I'm not going to write, well, no, I won't. So proof of theorem 20. I'm not writing it down this time because this theorem is not that much of a big deal. So proof is a good exercise. So we want to prove that n plus m is a Poisson process with the rate we're expecting. So remember, we have to prove A and B. Have to prove A and B. So A is that the number of events between u and v is given by a Poisson variable with parameter we're looking for, and B is that if we look at different intervals, then they're mutually independent. So remember that n, so for A, nuv follows distribution of Poisson with parameter integral from u to v of lambda of t dt, while muv is Poisson with integral of mu instead of lambda. And they're independent. And nuv and muv are independent. So by additivity of the Poisson distribution, we know that the sum is Poisson nuv plus muv is Poisson with parameter integral from u to v. So the sum of integrals is the integral of the sum, of course, like that. So no surprises here. proof for the A part is just we add Poisson variables and they happen to be independent, so the sum is Poisson. And for B part B, well, I won't write it down. It follows from B for N and M. Okay, so for N, disjoint intervals will yield to independent occurrences. Same thing for M. So if we add everything together, different disjoint intervals are still mutually independent. It's not worth writing down. Okay, so this is superposition. Add up independent Poisson processes and you get a Poisson process with larger parameter. No surprise. Now here's something which is a bit more complex. Marking. So sometimes we want to do the opposite. Instead of combining two different Poisson processes into a big one, we're interested in taking one and then splitting it into several smaller Poisson processes. To do that, we do marking, and we're gonna give each occurrence a mark. So what this means, so we're given a Poisson process, its rate is lambda of t, and we're gonna say that any occurrence, when it happens, is given a mark which is a number from 1 to k, independently of everything else, with probability p1, p2, and so on, pk. So, for example, you're at a call center and your calls arrive as a Poisson process, and you can give a mark saying that your call is, well, either, let's say, either a man or a woman is calling you, and say, well, each one happens with probability half, and so you have the marked process of calls by men and the marked process of calls by women, and probably you would then give P1 is half, P2 is half. Or, volcano eruptions, you can mark them by the amount of lava which comes out. If there's more lava than an arbitrary amount, which I'm not going to say, then you would say it's mark 1. If there's less lava than that, you would say it's mark 2. And this happens independently for each eruption. Okay, there'll be more about that soon anyway. So we write, now we had NUV, and I'm going to say NUVI, like this, is the number of occurrences of type I happening in this interval UV. So we have this for each I going from 1 to k being the total number of possible marks you have. And before I give you a theorem about this, we have an interesting lemma about Poisson variables. And we're doing the same thing with Poisson variables. I'm actually going to write this lemma down because it's quite involved and it's important that you understand what's going on. Lemma 21. So we're given a variable x. So let x be Poisson with parameter mu. And say that x is a number of objects. So, well, as we say, conditionally on the value of x, on the value of x, so value of capital X will be called small x. we have X objects. Maybe it's X phone calls, X objects, and each of those we're going to give them a color, a type, a mark, which have one of K types each. So each of my X objects can have type 1, type 2, type 3, or type K. And we assume that this happens independently, that the type of each object is chosen independently of the others. So, okay, so I throw my X random variable, let's say it's 3, then I have 3 balls, and for each of my 3 balls I'm going to choose its color with these distributions. So Pi equals probability of being type I. Probability of having type I. So for each ball, I choose its color, its type, with probability independently, and I with probability Pi. And now I'm going to let yi equals number of objects with type I. Okay, so one thing is that the distribution of yi is, well, if I have little x, then the distribution of yi is a binomial with little x tries and Pi probability of success. I'm thinking maybe we can zoom in some more. And we're actually fine. All right, yeah. No, this is not good. Better have a whole picture. Okay. And so the lemma says, the lemma is still visible, that these so I goes from 1 to K, these yi, it happens, it's quite surprising that they end up being mutually independent and all Poisson. Then the yi are mutually independent and yi has distribution Poisson of Pi times mu. So this may be a bit surprising, Pi times mu. This may be a bit surprising. Actually, I wouldn't be surprised if you've done an exercise like that last year or in your previous probability course, because it's very nice property of the Poisson distribution, and it does come in useful. So I have a Poisson variable, then I'm splitting it into lots of smaller variables by grouping each object with an independently chosen types. Then each of the splits is also Poisson with an adapted parameter since they have to be smaller, and then they're mutually independent. Let's prove that. Proof. So this, it's not difficult, but it takes a bit of writing down. So we want to prove, maybe I'll write what we want to prove first. We want to prove, we want to show that probability of y1 equals little y1, y2 equals little y2, and so on all the way to k. And this probability is equal to, I write it as a product, product for I equals 1 to k of e to the minus pi mu times pi mu to the power yi divided by factorial of yi. So this is what we want to show. So why is this what we want? Because each of those is the distribution of a Poisson variable with parameter pi mu, and if I'm multiplying everything, it means that they're independent. Okay, so let's do that. And the thing, of course, how do we do that? We use the fact that the distribution of these, y1, y2, yk, is given conditionally on x. So this is why we let little x be the sum of y1 plus everything. Because if these are all equal to those, then their sum must be x. And so the probability that I'm looking for, so I write it as for all I, yi equals little yi, is equal to first the probability that x is x times the probability that for all I, yi equals little yi, conditionally on the event capital X equals little x. So we split it like that because we can actually figure out what both of these are. So I'm going to make some space first. And so write this, P of capital X equals little x. So we know that. This is the Poisson variable. So we get e to the minus mu times mu to the x divided by factorial of x. This we know. And here's a claim. Here's my claim. So I have my x and I want to split it into k groups. And you know, the first group has y1 elements, the second group has y2 elements, the third group has y3 elements, etc. And the kth group has yk elements. And my claim is that the number of such partitions is equal to factorial of x divided by factorial of y1, factorial of y2, all the way to factorial of yk. And then if I have such a splitting, what's the probability of this happening? Well, it's p1 to the power y1, p2 to the power y2, all the way to pk to the power yk. So maybe you're not convinced by that, but let's keep it for a second. If we have this, then you'll notice that recombining things, we go back to here. And I'll write that in a different color. I have a blue pen. So if I call this star, this thing is equal to star. Because as you can see, the factorial of x goes away, and then in the bottom we have each factorial of y's. We have the pi's to the power y's. Then mu to the x, you can split it into mu to the y1 plus y2 plus dot dot dot. So you're going to get each mu to the yi. And then here again you have e to the minus mu. So you use that 1 is equal to the sum of pi. So you're going to get e to the minus pi mu for each I. And then you just combine things. Okay, so y is the number of ways of splitting x into k subgroups with sizes yi equal to this. Well, you know it when k equals 2, right? This is the number of combinations. So if I want to split x people into two groups, one with size y1 and another with size y2, this is basically x choose y1. So it's factorial of x divided by factorial of y1, factorial of y2. And with factorial of y2, well, y2 is x minus y1. So we can use this repeatedly. That's one way of doing it. So p of x equals x doesn't matter here, but we can say, well, first choose the elements of type 1. We're gonna get x choose y1 times p to the y1, p1 to the y1. Then choose the elements of type 2. We're going to get x minus y1 choose y2 times p2 to the y2. Then choose the number of people of type 3. X to x minus y1 minus y2 choose y3 times p3 to the y3, and so on. And the last term will be, well, it's going to be, interestingly enough, just 1, but I'll write it anyway. X minus y1 minus dot 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 minus yk minus 1, choose yk. This is actually 1 because the sum of those is yk, times pk to the yk. If you write each of these number of combinations in terms of factorials, you get factorial of x divided by factorial of y1 factorial of x minus y1, and it's going to cancel out with the factorial of x minus y1 here. So you get factorial of x divided by factorial of y1. Then at the bottom you have factorial of y2 times factorial of x minus y1 minus y2, which cancels out with the factorial of x minus y1 minus y2 here. So we're left with just this, and so on. So this is one way. So what we're doing here is we're describing what we call a multinomial variable, which is generalizing the binomial variable with k groups. Okay. So we're done with this lemma, actually, because this is what we want. The end. And now we can use this lemma to get our interesting thing about marking Poisson processes. So theorem. So I do my marking thing with the Poisson process. So each event I mark it with probability pi to be of type I. Then the process given by events of type I is also a Poisson process, and its rate is the previous rate multiplied by pi. And each of those, so I've got k possible values for I, each of those are independent. And we don't really need to prove this anymore, because the proof would be let's show A and then let's show B. for let's show A, it means we have to show that the variables of Poisson, and it's a direct consequence of the lemma, because NUV becomes split into these NUVI's with exactly the same rule as this lemma. So the NUVI's are independent and have the correct Poisson distribution. And property B again follows from property B for the original process. So no problem here. Right, so we're saying, if you take your phone calls and then split them according to whatever characteristic of the caller you have, then each of those split processes are independent and are Poisson with a different parameter, which is the original multiplied by the probability of being the certain type. Okay, so actually we said P1, P2 is a probability of being type 1 or 2. These can also be variable. Nothing changes. This is all fine. And in the generalized version of this, we get independent processes, and their rates are P1 of t times lambda of t, and so on. And finally, we're ending this section with thinning. So thinning, you could say it's a special case where k equals 2. You don't really have to. The point is, you only remember one type. So I choose to only remember eruptions which have a temperature higher than 1,000 degrees. And I forget everything else. So, if an eruption has a temperature higher than 1,000 degrees with probability P, then the Poisson process of those eruptions it is a Poisson process, and its new rate is P times lambda. So same thing as before, just we only remember one of the things. And all right. So again, another useful thing to do with Poisson processes. And let's do this example because there's really nothing interesting in it. And then we will stop for today. So, example, university applications. So, suppose, example 35. So, suppose I'm a staff worker at the University of Sheffield and we get applications for maths. Suppose applications for maths happen as a Poisson process, so capital P, with rate lambda of t. And suppose an application coming in at time t has a probability P of t of being for a BSc, and if not, so if it's not a BSc application, then it's a master's application. If not, then it's an MMath. So we can mark those by saying, the first type is the BSc, the second type is the MMath. Marking those gives us two independent Poisson processes. So So the process of BSC applications. This one has rate lambda of t times p of t. And the other ones, math applications, the rate is lambda of t times 1 minus p of t. So the complement, so that it adds up to lambda. And sorry, I kind of moved out of the way. So my applications come in as a Poisson process with total rate lambda of t. We split those. Each event is with probability p of t a BSC, with probability 1 minus p of t it's an math. And so if we split them with the marking, we get that the BSC process has rate lambda times p, and the math process has rate lambda times 1 minus p. And that's all there is to say about this. This is how you do your splitting. And alright, we'll stop here for today. So let me tell you, you can move on with the exercises. Let me just have a quick look at which exercises you can do now. And then I'll set up the office hours. So 48, 49, 50 were fine. 51 is now fine as well. 52 uses a thinning, so you can do this now. 53 is a variable rate, so that's fine. 54 is a variable rate. I think you can also do this. And we have to stop at 54. So you can now work on the exercises up until 54. Perfect. And finally, I'll set up the office hour. Is the link. I will copy this in the stream chat and in the video description. Oh, this has the previous. That's an error on my side, which I copied accidentally. And we're fine. So I will see you on Tuesday at 12. And of course, you can ask your questions at the office hour right now, or you can send a message in the message boards. And if no questions, then see you next lecture. Bye.